Yeah.
Isn't that?
That happens. That's all.
Wow, calculus.
All right.
Yeah, front cover.
Oh, guess who's
That's a group picture.
yeah, what's the front cover? Why do you
Yeah,
get to be on the cover?
I don't know. Somebody gave it to me today.
Was that where they were at the juniors or at the juniors? Yeah.
He thinks he's cool because he's
In
on
a fire truck. Wow.
You're basically a local celebrity.
That's what
That's what I'm trying to say.
Well, that's a big deal.
Yeah.
All right, so, and again, how much of this you write down, whatever, it's up to you. We're going to be adding to this. You notice on the notes here, I put like a 1 by that. We're going to be, at some point along the way, we'll have a variety of different methods for different types of volumes we want to find. And so, and the other thing you notice is we're talking about volume of a solid, like the lemon. We wanted the volume of the solid. When you're in geometry class, you do volumes. That's usually empty space volume. Like you have a pitcher of water. How much water can it hold? How much empty space is in there? I guess, if you filled that with a solid, that would be the same. I mean, but the thought of empty space kind of becomes an important issue here today, I guess is what I'm trying to say, is that if we had an object that was solid, but then part of it was drilled out. So for example, if I drilled out part of this, then we would not be counting the empty space. We want the volume of the solid material, okay? With the idea being an application of this would be an engineering kind of thing, designing parts and things that, if you had to do a cost analysis on this piece that might be a part of some other larger thing, and you have to do a cost analysis, well, you need to know how much plastic or whatever the material is. You need to know how much is in there, and to be able to do that. All right, and so these ways of setting up formulas and generating those things is a way that some of this is done. So this idea of doing it by slices. So yesterday what we did, we sliced up those lemons and we said, okay, what's the volume of one slice? We said it's kind of cylinder shape. What's the volume of 6 slices, 10, 100? What if you had 1,000,000? And so what we found out is that if you add up any three-dimensional object, like what we had were these little cylinder-shaped things, well, the volume of a cylinder is pi r squared times h. Now here I just put pi r squared because that's the area of the shaded part because it's a circle, and then the h was the delta x, the dx, and that's what that turned into. So the formula ends up being area times the width, and the dx is the width. So if we have the area of the slice times the infinitely small width, that gives you volume, right? So that's area like centimeters squared times centimeters, that would give you centimeters cubed. So what we have here are the volume of the little slices, and then the integral adds up all those slices. And so that's how we get the total volume. All right, so that's the formula we're working with right now. What we're going to do is generate a list over here of different types of slices we could have. Okay, in other words, any object that we can slice either this way, that's what 9 and 10 was like, or this way, and every slice, the shape is the same, then we can do this method. So if you look at this thing here, every slice I make going this way is going to be circular shaped. So it's going to have like what we call like cross sections. Okay, like cross sections. So as long as that's true for that figure, then we can use this technique right here. All right. So what we're talking about right now are things that have circular type slices. Now I've got a thing here that I can show some examples that will help maybe this to make a little more sense. So here's kind of what we had yesterday. Pretend that this was sort of like the lemon, you might say. But we're going to take that pink region and we're going to revolve that around the x-axis. Okay? So this would be like one of the lemon slices. Now notice that our slices, remember we called them cylinders, but they weren't really cylinders because they were kind of rounded here. Well, that's what we were kind of pretending they were, and we used the average radius and all that stuff. So if I show all of the different slices, so this would be like 5 different slices here adding up. Now that's an approximation, but if we did 10 slices or 100 slices or 1,000 slices, then each of those slices would be better and better approximations of this actual solid. Okay, so that's the idea of what we're doing here, to find the volume. All right, so if I go over to this page, so now if we do an infinite number of slices, so same picture, but now we're doing so many slices that they're just paper thin. Now when I revolve this, okay, we can see the solid that we create, and we can see the slice. Okay, and again, we can sweep that through there, and so our slices, so our integral goes from 0 to whatever this number is out here, looks like it's about 9, and the slices fill the space from 0 to 9, so we set up our integral. Okay, the other thing we went over yesterday, and we talked a lot about, was the strip. Okay, so if I revolve this again, it's clear to see that this strip right here is what part of the slice? The radius of the slice. And we just got to doing the area problems where we talked about top minus bottom and right minus left. So if you do the top y value here times the bottom y value here, and let's go ahead and do that here real quick. All right, if I take the top y value minus the bottom, oh, I'm trouble there, but this is y equals square root of x, so the top y value is square root of x, the bottom y value is down here 0, and every strip I draw here, that would be the case. Okay? So that is, and so what you'll see me do a lot today is take this as my strip, and the axis of revolution would be here, and so they're always going to be perpendicular to each other. So if the axis of revolution is horizontal, then the strips are going to be vertical, because this is going to go like so. So as it revolves, this is the strip, and you can see that that creates a circle. And you can also see that that marker is the radius of that circle. Okay? So the way I would like you to, you'll see later on today as we go through this why I want you to do this, but I want you to label that. So I want you to write that out and say, okay, R, this strip, is the radius. And so then back to this formula we had here a minute ago, okay? So the area of that slice is pi times that radius squared. All right, so pi times that radius squared. So pi times that radius squared. And then the slices that we're going to add up go from 0 to 9. That would be the integral for the volume. And it gives you volume because this here is area times width gives volume. All right, and that's what's happening with that problem. So that was essentially what we were talking about yesterday. So now, if you want to go to number 9, number 9 had this shape, right? And it was telling you to revolve around what? The y-axis. Now up here was this line, and this was the point, what, 2, 4? Okay, and it wanted you to revolve around the y-axis. So that is going to create, well, here, I've actually do have a picture of this. If we go, it's this right here. Okay, it would be this right here. Let me move this up so it looks a little more like the picture on number 9. Okay, and so what we're going to do is we're going to revolve that region around the y-axis. So it should be very similar to the problem we were just doing. Okay, the one we were just looking at. It's a similar picture, it's just up here instead of down there, but we want to use the right x's and y's, those kinds of things. But look at the slices. The difference is the slices are horizontal, right? So, difference, axis of revolution is now this way, so a slice is perpendicular to it, so it's going like so. Okay, it's going around like this. And you see that the marker, again, is the radius. The strip is the radius. All right? So, and then if we look at all the different slices, this time now, just like before, when they're horizontal, they're going to go this way. Okay? So that's still that, so that's that basic problem. Okay, so they drew in a strip like this, right? So this is the line y equals x squared, but we don't want that. Whenever we're doing a horizontal strip, we want the x, the right x minus the left x. And that's our radius, like we said. That's going to be the radius of our slice. If we draw the other half, you don't have to. But if you want to draw what this thing would look like, sometimes that can be helpful. So here would be a slice right here. So if you want to draw in a slice, if you want to draw that picture, if you can see that, I'll be honest, I was always bad at those. Now I've taught this long enough, I'm getting better at these, but these three-dimensional things are not as easy to see. You don't have to draw it, but that is your radius. So what's the right x coordinate here? Square root of y. We have to take this equation and we have to solve it for x. Now, when you solve it for x, you actually get plus or minus square root of y. Well, what's the minus? Not bottom, but the left, right? So when we do a plus minus, it's either top half, bottom half, or it's right half, left half. So when we're doing a solve for x thing, we get a plus minus, it's right half, left half. Well, we're on the right half. So it'd be square root of y. So the right x coordinate is square root of y. The left x coordinate is 0. So that's our radius. So our integral, and I usually put the pi out in front. Pi r squared, so there's r. And it goes from 0 to 4. The strips fill the space from 0. Oh, and I put a dx in it. Yeah, that's bad. That's bad. Don't mix x and y. And then the other thing to keep in mind is whenever you have a horizontal strip, we said this before, it's still true. Whenever you have a horizontal strip, it's in terms of y, because it's delta y width. It's dy. The horizontal strip's always going to be dy. If these are y's, then these numbers have to be y's here as well. Strips fill the space from 0 up to 4. All right, and is that the one that was 8 pi? Okay. All right, and then what was number 10? What was that picture? Oh yeah. Now that was and somebody in the other class asked me this. They said, well, could we just do this with x's? They did this. Let me draw this in blue. A couple people in the other class, I think we might have talked about this. A couple people in the other class just did this as if it was y equals square root of x, like that. And then they went from 0 to they went 0 to 4 over here. Okay, they just inversed everything, and they revolved it around instead of the y-axis. They just revolved around the x-axis. Yeah, it's the same thing. It's the same picture, it's the same shape. Instead of standing up, it's laying down. But we don't want to do that, right? We want to do it the way they give it to us, okay, with the x or the y. And so we want to make sure and set it up that way instead of doing that inverse relationship. All right, so on 10 we got a half circle or a quarter circle, all right, and they put the strip in this way. Well, that means you're going to revolve it here. So the other half's going to be over here. So what you have is a half a sphere, right? Half of a basketball, half of a volleyball, whatever. All right? But when you do that, you need to solve for x. So you need to really take this equation, solve for x. Well, it turns out when you do that, you end up with, the very same equation. I mean, because of the symmetry, you end up with the very same equation, just in terms of y. Okay? But that's what you want to be able to do. Okay? So it goes from 0 up to 4 and so forth. All right. Let's do this next. Now this is going to be very similar to what we just did. It's going to be very similar to one of these, but you're going to have to draw the picture yourself, because starting today with these, whenever you're given one of these, almost never will you be given the actual picture first like you were here. You're going to be given the boundary. You're going to be given the region, okay, bounded by this, bounded by this, bounded by this, and then it's going to be revolved around this. Find that solve. Okay, so we're going to do one of those. Oh, time out. That's there's something else I need to do first. Okay, so back to this picture here, right here. All right, let's move this axis of revolution now. Okay, now let's say the axis of revolution is here. Same region. Now think about this. This is how this would be given to you. You would be told to revolve this region, the region bounded by y equals square root of x, y equals 0, x equals 9. This is what you would be given. And then revolve that about y equals -2. That's what you would be told. Okay, so here you come, you graph y equals square root of x. You graph y equals 0, which is the x-axis. You graph x equals 9, which is this vertical line here, and you'd say, okay, there's my region. I'm going to revolve that region around here. What's different about this one? Has this section in here of empty space. Now try to just take a second to picture this solid. Picture the three-dimensional shape here, if you can. Okay? And then what would the slices look like? So it would be this way, right? That would be the slices, and that's where this came from. Okay? Ryan didn't like me bringing his favorite toys.
I love playing with this.
So anyway,
Wow, you just gonna drop it
So anyway, but that's the idea, right? That's the idea. There's going to be some empty space. There are going to be donuts, washers, rings, whatever you want to call them. Typically, they're called washers. Now, you notice in a lot of books, this is called the disc/washer method because when we go back to our when we go back to our that's why I call this a disc. I mean, cylinder, circle, whatever you want to call it. But this is often called the disc/washer method. If there's no empty space, when we talk about a disc, we're talking about a solid. The slices are solid all the way through, just like the lemon was. Okay, just like these would be if you slice these. They would be circular, solid slices. But if you slice this, you know, you've got this empty space, and we don't want to count the empty space. So what is, first of all, let's look at it. So you envision that. So let's revolve it. See if this is what you were seeing. Okay. And if we look, so again, what we want is our integral to add up the volume of all of those rings, all of those washers. Okay? So, oops.
What's going on?
There we go. All right. All right, so while that's going, let's talk about what is the formula. Well, if we come back to this, we need the area of the slice. Okay, well, if the slice is a washer shape, let me see if I can draw one. And we'll have these in our notes again at some point, but okay, it's possible that the slice is a washer, a donut. What is the area of a donut, a ring? Area of the big circle. So let's call that big R. And minus the area of the little circle. Let's call that little r. So it's going to be pi big R squared minus pi little r squared. That would be the area of the ring. That's where the solid material is. We don't want to count the empty space. So it's the whole circle minus the inner circle, minus the empty space. Now for our purposes, we're going to factor out the pi. And then we can pull that on the outside of the integral, just like we've been doing. And then what we need is big R squared minus little r squared. Now here's where it gets really important to write down big R and little r. Just like in these earlier problems, I was writing down what R was. Right minus left or top minus bottom. Remember, the radius is going to be a strip. It's either going to be a horizontal or vertical strip. So we're going to do top minus bottom or right minus left to get that. Okay? All right, so back to our other notes here. So our area of a washer is going to be pi, parentheses, and then big R squared minus little r squared. So you can see we have to determine what type of slice is created in our solid. If we know what type of slice it is, then we'll have a formula for the area of that slice, and we'll stick that right into our integral then, and that will give us our volume. Much like we did arc length. We had a formula for arc length, which came from the distance formula, and we stuck that into our integral. Well, now we're doing formulas, area formulas, but then times the dx width piece gives us volume. All right, so if we go back and look at this, okay, again, our integral would be adding that up. All right, now, those are the two types of slices we'll deal with for right now, because these solids we've dealt with up till now, and we'll get into some others tomorrow, are called solids of revolution. They're all solids created by revolving a region. Anytime you revolve a region, you're going to create a circle. So these are the two types of circle slices we're going to deal with, either solid circles or circles with a hole in them. Okay, either discs or washers. All right, so the problem I would like you to do or attempt is going to be this one right here. It's actually two problems in one. This is like our homework. You know the old homework when you got a problem but it's got like 4 parts to it? Well, what we're going to do is you're going to have this same region, but we're going to do 2 different problems with it. So we'll just go with the first one first, and we'll do that one and check it over, and then we'll do the second one. And the difference here is we're just going to revolve the region around a different axis. Okay, so what the problem is we want to draw the region bounded by these 2 equations. So go ahead and do that first. Draw the region bounded by those 2 equations. All right, now we're going to revolve that region around the y-axis. Now, there's something that is a little bit of an issue we haven't seen yet right now. What is it? Is anybody noticing something strange here? Well, first of all, is this the region you got? That's the correct region. So what's different about this one then? It says to revolve about the y-axis. Logan? In the past, when we took the lemon and all the other problems, we only had half the region and then revolved it, right? So if we revolve this around the y-axis, it's just going to revolve onto itself, right? So wouldn't it be the same if we just ignored this half and just took this? Okay, somebody in the other class asked it this way. They said, well, can we just assume it's first quadrant? No. If they give you this region, if they say it's the region bounded by y equals x squared and y equals 4, you graph y equals x squared, you graph y equals 4, and you don't assume it's just first quadrant. However, if they ever give you an axis of revolution that's right in the middle like this, and when you revolve it, it revolves right on top of itself like that, then yes, I would just ignore this half and just use that half. And you actually could do the left half, but that doesn't make sense because then you have negatives, and then it just makes it more confusing. So I would go ahead and just use that half. Okay, now, so we're just going to pretend it's this half. Now, the next question is, and these are kind of the order that you ask these questions yourself. First you get the region, then you say, okay, I'm revolving it. Now, one of the very first questions you ask then is this horizontal or vertical strips? Horizontal, it's got to be, because like I was saying earlier, if your axis of revolution is perpendicular, the strips have to be vertical. If your axis of revolution is vertical, then your strips have to be horizontal. They're always perpendicular because the slices are always taken, and that's what it'll say. It'll say with cross sections perpendicular to a certain axis. Okay, so or it's revolved about a certain axis. So this has got to be perpendicular. So we have to do horizontal strips. Okay. The second question you ask yourself now today that you didn't ask yesterday is there going to be any empty space? And the answer is no, right? Your slice is going to look like that, right? It's going to be solid. So there's no empty space. So we are dealing with this type of a slice right here. Okay? All right, so this actually is like number 9 then, isn't it? Isn't this basically number 9? Okay? Where we have to change this to x equals square root of y. And so our radius is going to be, what's our radius? Square root of y minus 0, right minus left. It's the right x-coordinate minus the left x-coordinate. So this x-coordinate is square root of y, this x-coordinate is 0. And so now our integral, since there's no empty space, we just put pi on the outside if you want. Take your r, square it. So it's pi r squared. The strips or the slices go from 0 to 4. And then wouldn't this 8 pi? I think it's exactly the same thing, isn't it? In the end, it ended up being the same thing. Okay, now, you guys try this one. Number 2 here. Now we're going to revolve it around the line x equals 2, which is this line right over here. And we're going to revolve this whole black space now around the line x equals 2. Give that a try. Talk about it if you need to. First question, horizontal or vertical strips? Horizontal. It's still a vertical axis of revolution, so they have to be perpendicular. Second question is empty space. So it's a washer, kind of a slice, which means you have a big R and a little r. So you need to identify what big R is and what little r is. Okay, now, I'll help you out on this one a little bit, and then we'll go into another one here where we're going to do talk about this. But here's what I've got. Now, you don't have to draw this. You do not have to worry about the three-dimensional shape. But isn't this kind of what it is? Like somebody in their class, because this is right before lunch, they thought it was a butt cake. Like a butt cake. You ever had one of those? The round with kind of the whole thing in the middle? Now, there would be empty space. So if we would have done, instead of x equals 2, if we'd have revolved around x equals 3, there would have been some empty space there. But there's still this empty space here. Now, that's not the greatest picture in the world, I understand. But anyway, for what it's worth. But, and here's a slice. But I think what sometimes people have trouble recognizing, and all kinds of people see different things in these pictures, but no comment, but I see a butt kick. Okay? Your mind's out of the gutter. All right, so the radius, the big R and little r, people have trouble with that. Here's, I think if you draw the actual washer, then it's not so bad. You can see that the outer radius goes all the way out to there, and the inner radius is right in here. If you draw the actual washer, you can see those. But here's the thing, I don't think you always want to draw the whole three-dimensional thing. So I think what you've got to recognize is this, couple things. A radius always comes from where? The center. The radius always comes from the center. And when we revolve these things, where's the center? The axis of revolution. Whatever the axis of revolution is, that is your center. So the radius, the strips, always have to come from there. So what's interesting about this is in the last problem we did, our strip was inside here. Does that tell us anything? Does that strip actually give us anything? Is that a radius? Is this strip a radius? No, because it doesn't touch the center, right? So we're used to our strips being inside the region. Well, guess what? On a washer, they are not. These are the radius, the big R and the little r. You have to draw in your own strip, so you probably will not even use this strip in here. That's just the difference between big R and little r, which we don't want. We want big R squared, or I wrote it in that other page, big R squared minus little r squared. So we have to identify big R and little r. So I actually drew them in myself. Now, again, once you draw out this whole thing and draw in your washer, you can kind of see, oh yeah, big R goes from here out to here, and little r goes from here to there. But but I don't think you want to have to draw this every time. So what you recognize is big R is always from the center out to the outer edge, and little r is from the center to the inner edge. And so once you understand that, then you can just draw them right on here. Center, from the center to the outer edge is big R. From the center to the inner edge, that's little r. So let's write that down. So what's big R then? Now remember, we always go right minus left for horizontal strips. So what's the right x coordinate? 2. What's the left x coordinate? It is negative square root of y. Remember, this parabola is y equals x squared. Since we have horizontal strips, we have to do plus or minus square root of y. And we said the negative square root of y is the left half, positive square root of y is the right half. So this half over here is negative square root of y. This half over here is positive square root of y. So we're going to go 2 minus negative square root of y. And our little r is going to be from the center, right minus left, so it's going to be 2 minus positive root y. So this will turn to a plus. So there's big R, there's little r. So our integral becomes pi out in front, big R squared minus little r squared dy from 0 to 4, because our slices are going to be washers, donuts. The area of a donut is pi times big R squared minus little r squared. We wrote down big R and little r here. So you got to build your integral in pieces, and I think to make the most sense. And so that's why I like writing the big R, little r. And again, what are these? They're strips. Now, they're actually strips you have to write in yourself. But remember, radius always has to come from the axis of revolution. So when our axis was the y-axis, then yeah, that was our radius right there. But not in that problem, not in a washer. You have to draw in your own strips for big R and little r. All right, so you go ahead and work that out, and it comes out to be something. Anybody do it? Anybody type it in? What'd you get? Ooh, is that the same answer as 10? But it's not the same. I mean, it's not the same region, right? It's not the same region or anything. That was half of the sphere. It's kind of interesting to have the same. All right. So now you guys try this this region right here. Now that's it's here's the region. First, you're going to revolve it about x equals 1, which is a vertical axis of revolution, which means you'll have horizontal strips. Then you're going to revolve it around y equals -2, which is a horizontal axis of revolution. So you'll have to have vertical strips for that one. So you have to keep those straight. Okay, let's try those. I would recommend drawing separate pictures for each part. It's not mandatory. It just gets kind of messy. I'm able to do different colors, which kind of helps. But
All right, how about the first one? We getting an answer? Somebody want to throw something out? Yeah, let's put it on a calculator. Anybody put it in yet? What are you getting? 11 pi over 30. Okay, so the red would be the part you'd be interested in here. If you're getting 11 pi over 30, want to go on to the second part, that's fine. But the red line is the axis of revolution, x equals 1. So our strips, our radius, our slice is perpendicular to that, so it's got to be horizontal. So your outer radius, again, radius always comes from the center, so it's got to come from the axis to the outer edge. The inner radius goes from the axis to the inner edge. So, what's that?
Solve for X.
So you have to solve for x. Anytime you have horizontal strips, here's why. Because what are you subtracting here? To get this length, it really comes down to basic arithmetic. To get that length on a horizontal strip, you're taking an x coordinate minus an x coordinate, right? This x minus this x. What is this x? Well, it's 1. What is this x? It's the x on this equation, y equals square root of x. So we've got to solve for x. So x equals y squared. So the x here is y squared. Yes, probably the number one difficulty in the early stages is remembering you've got to be x or you've got to be y. Horizontal strips, you solve for x, your integrals will have y's in them. Vertical strips are the reverse. So you write down, so you build it then. So you do big R, you do little r, all right? And again, then your strips fill the space this way from 0 to 1. Now they happen to meet at 1, 1, so they're going to go 0 to 1 no matter which way you go. But understand that we're going from bottom up to top. We're filling our slices. Our slices here are going 0 to 1. And don't forget the pi out in front. So I agree with 11 pi over 30. Okay, now go ahead and try part 2. All right, some of you are finished. What are you getting? 49 pi over 30. Now, another thing where this came up in the other class was the answer to that one is bigger
than the other one. It's that same region. So why, I mean, this is revolving this way, this one's revolving here. Why is it so much bigger? I mean, 4 times as big. Yeah, this extra space here, think of it this way. When this comes up off the page and revolves, this comes clear out here and then down and then out and around. So this region is creating, as it comes, as it sweeps around there, creating all this solid that's going around here, whereas this is just revolving right there, right? There's that empty space, but it's not making near as big an arc. You know, it's kind of like when you ever, well, or you ever have a line of, you ever do this with a line of 4 or 5 people and you spin around and around trying to throw the, I don't know, what do you call that even? Whip the people around the edge, you know, you hold hands and you swing around like this, and
Yeah.
the people on the outside, you'll fly it because they get going so much faster, right? The longer you make that, the longer, you know, an arc you swing out. If you only got like 3 people, you just make this small little circle, right? It's the same idea as you extend this out. So the amount of solid is just that much more, even though it's all being created by the same region, okay? So, yes, I agree with 49 pi over 30. So you can look at the work here. But again, since you're revolving around this horizontal axis, the strips have to be vertical, like so, okay? And you've got this empty space. So your outer radius, your inner radius always comes from the center, top minus bottom. Now, somebody in the other class had these backwards. Well, why did we do top minus bottom and right minus left? So it'd be positive. So your radius would be positive. If you do them backwards, your radius is negative. But then again, what do we do with the radius? In our formula, we square it. So does it matter? It doesn't really matter. Now, but I think as a habit, you want to do that because we're going to get into some slices when we do the strips. They can't be negative. And then that'll throw you off. Well, actually, it'll probably just make the answer negative, and you'll say, oh, I must have done it backwards. Okay? So just get in the habit of top minus bottom, right minus left. You'll be better off. All right. So here's what those would have looked like. Here's what the first one would have looked like, more as a solid, right? Kind of a bowl-shaped thing with some empty space. So there was the washer. This would have looked more like this because you'd have had that empty space, you know, because the line was down here. Again, I don't think it's a big deal that you try to picture those, but if you like doing that and you want to try to picture what they look like, that's fine. Here's your homework. It's 8 problems, okay? Number 13, it's in that same LH packet that you had. You can get a lot of it done, I think, today here. 13 is 4 problems. They give you a region, just like we got done doing, and then they have you revolve it around 4 different things. Now, I think you should have 4 different pictures, but I'm not going to probably count off here when I look at it if you don't. But it just gets real messy with your strips and things like that. Okay, but 13 has 4 different problems. 15 gives you a region and then has 2 different things to revolve it around. And then 22 and 25 each just are 1. All right, the book does a really pretty good job, and so I've got this opened up here so you can come up and check as you go along. It does a pretty good job of showing the big R, the little r, showing the pictures, giving the answers. So if you want to check and see that you're on the right track here as you work on this. Tomorrow, we'll add to our list of slices, of different types of slices and how we can look at those. Is anybody going to be gone tomorrow? Anybody gone tomorrow? Okay.
Are we doing anything important on Friday?
Friday, we're going to do some in a new packet. Well, we got done with that sample 3, and so sample 4, which is might be our last of the big packets, like practice test kind of thing. So we'll be starting on that on Friday. And then, yeah, I'll probably have to do another sample pack if anybody wants one, especially people who are taking the AP test. If there's anybody taking the AP test and wants to do one more before that. But okay, Go ahead and work.